Welcome. Today we start with introduction on laser cutter, one of the most popular machine in Fab Lab. Very easy to use, very fun. You can cut so many materials. So the objective of today is just to understand how the machine works and give you some example. And we will get into tutorials and how to actually use it in a project a bit later on. So let's start with a very quick presentation. This presentation is actually available to everybody if you're interested in. So what's a laser? A laser is just a pretty powerful light that when you focus on a very small spot, it gives you enough energy to burn or melt the material. So what happened, you can see it here, it's pretty simple. You have the laser source that goes through a lens. The lens focuses the light on the material, and you have a blow of gas in the most cheap laser cutter. Typical machines from Fab Labs is just compressed air. This flow of air keeps the lens clean, so it blows away the smoke. This is very important because the lens is transparent, but the smoke is not. So if the lens gets stained, the laser will actually laser cut the lens instead of the piece you want to. And even if you don't get to damage the lens, that is actually something you don't want to do. Usually lenses are pretty expensive. But even if you don't damage the lens, you definitely lose power. So we want to keep the lens cold, we want to keep it clean, and a constant flow of air is the easier way. Now, the second reason why we have this flow of air, in some materials, it helps the process. For instance, with wood or other materials that burns, the oxygens that we blow through the air is actually speeding up the burning process where there's enough energy to cut it and to burn it away, and cool down and turn off the fire, let's say so, on the borders, on the part where you don't have enough energy to actually burn away the material. So this is very simple configuration, as you can see. Changing the power, you go from cutting paper or fabric to metal. The concept is similar. Sometimes the laser source is different. The most common one is CO2, but you have fibers, we have other tons of different kind of lasers. We don't care that much at the moment about those differences. Just keep in mind how this thing works. Now, there is another important thing about the fact that you have a lens here, and that means the laser must be at the proper distance from the piece to get a good cut. We will get to this in the tutorial parts. So let's just move on at the moment. Now, when you burn material, you basically burn a part of the piece. So just to explain what I mean, let's say that we are laser cutting a square part, something very simple, like let's say this. Now, if we zoom in, when you laser cut this line, what happens is that you're burning away a certain amount of material, maybe not that much, few tenths of a millimeter, but the cut is not going to be a single line like a cut made with a blade. We are burning away material. So what happens is that you have two parts after you cut it. You have the piece you wanted, of course, but you also have the leftover. So this line could be to cut a square out of a piece, or it could be to make a square hole inside a larger panel. What you have to keep in mind is that if you design this piece, let's say 40 millimeters by 40 millimeters, so 40 by 40, what you get, the piece is not going to be 40, it's going to be a bit smaller, maybe 39.6 or 39.8. It really depends on the quality of the laser, but it's not going to be exactly 40. The same way, so this is not, let's say 40 by 40, but for instance 39.8. And in this case, it's not going to be 40 either, but a bit bigger, so 40.2, for instance. Now the numbers, as I said, can change a lot based on the kind of laser, the thickness of the material itself. But in general, the rule is the same. The piece you cut away gets smaller, the hole you make gets bigger. That's always going to be the same. The fun thing is when we get to 3D printing, you see it. When you 3D print something, is the other way around. So when you print a hole, the hole usually gets a bit smaller. And when you print a piece that should fit in the hole, the piece is usually a bit bigger. What's that supposed to mean? It's very simple. When you laser cut, you don't have to worry to fit a piece inside another. So if you laser cut a circle that is 30 millimeters in diameter, and you laser cut a hole that is 30 millimeters in diameter, the two pieces will always fit together. There's actually going to be a bit of a gap, and the two pieces can probably move a bit, one inside the other, but beside that, you have no problem. When you 3D print something, on the other hand, is completely different. So get ready to do a bit of math when we start to speak about it. So back to the presentation. The first thing you do with a laser is to cut. That's a very simple thing to do. Every vector in your design will be followed by the machine, and the laser will cut through the material, or partially if you limit the power. We'll see what that's supposed to mean. But just with this basic operation, you can actually do a lot of things. So this image you see on the side is actually from an artist that made this three-dimensional sculpture, laser cutting different bills of $1. The final result was pretty amazing. As we said, the part that you cut away is very often called the kerf, and it can go from 0.1 millimeter in a very good laser to 0.5 in a very bad one. In average, 0.2 of a millimeter is a good approximation, so 0.2 or 25. There is a way to test your laser, and we will actually do it with the one you have in the lab. First thing you can do cutting pieces is to put them together to create a frame, a structure. Now, lasers allows you to have very precise parts. So even if you want to make something that moves, it's easy to create mechanisms. In this case, you see you have screws that works as hinges in a pretty complex robot. On the other hand, you can create pretty rigid structures from simple panels just because you snap them together, you screw them together, or glue them together. The most common way to join two pieces that you laser cut is this. So first of all, you never ever cut something straight. When you want to join them together, you have to make these snaps. The reason is actually simple. If you think about two pieces of wood that you cut and you try to create a connection between these two pieces of wood, you will never be able to get something very precise. Now, it's tough to show you, but think about something that could slide back and forth or turn a bit. It's really something not easy to align. While when you have a connection that is actually a puzzle, the position, the relative position of the pieces is always the same. So it's easy to snap them together, and it also increases the amount of glue or connections that you can have, even mechanical, just because of the relative movements that is limited. So whenever you design something that you want to be a rigid structures, please do that. The connection could be perpendicular or not, could be could be symmetrical or not. The angle you get to optimize the overlap of the cuts is always perpendicular. There are ways to get different angles, we'll get there, but in general keep in mind that the best way, the easier way to glue things together is to have them perpendicular. About the symmetry, now in this case and in this case, this piece here could be flipped. So you can assemble it the other way around if you want. This could be useful, for instance, if the wood is damaged or not beautiful on that surface. In this case, you can't. In general, if possible, being symmetrical make things easier. It's not always possible, so don't worry. And sometimes you need not symmetric parts just to be sure that people will assemble it in the right way. Not just people, even you. It's very easy to get confused when you have a lot of pieces on the table and you don't know exactly where to start from. So I'd like to give you a very simple example of what could be done. Oops, sorry, there could be a glitch in the video. I will try to cut it out later on in the editing. Anyway, I was saying I want to give you an example of something that could be done with a laser. It's a very simple object. I will bring more elaborate and complex things later on. Now, this is a very simple box. It's very common to have boxes when you laser cut things. It's the easier thing to do. There's actually softwares online that allows you to design this without even thinking about it. If you check, let's say, one of the connections, okay, you can see the pattern of the pieces. Now, of course, in this case, being symmetrical makes no sense because on one side I have this kind of line and on the top one is smooth. But the bottom of the box, well, the bottom of the box is actually symmetrical. So I could have flipped it, rotated or flipped it, and it would have been assembled anyway in the same way. For instance, something very common for laser cutter is to ruin the wood this way. So those stains you see are smoke stains. You can sandpaper those away usually, but if you don't want to, if you don't need it, you leave it there. You just pick up the most beautiful parts to keep it visible and you leave the rest inside. So that's just a very simple example, but it gives you an idea of what it means to have the connections and what's going to be the final result. Back to the presentation. The assembling can be done in different ways, so not just on the border, but on the center as well. This is what we were talking about symmetry. This piece can be assembled this way or that way, the opposite way, and there's no way to know which one is the right one. In this case, it's enough to move the connection and everything becomes much easier. So it's pretty clear that this is the right way and this is the wrong one. Keep it in mind, it's very useful to do that. Simple example, a dies. you know that the opposite faces in a dice should be 7. So opposite to 1, there's the 6, opposite to 5, there's 2, opposite to 4, there's 3. To be sure that this gonna happen, no connection here are the same. Very simple example, but it gives you an idea. As we were saying, in particular when you want to create something robust out of a simple material, create a lot of ribs and structures inside is the easy way. My suggestion is to stay on the simple solutions. We'll see these things very fancy, but not exactly practical. We'll get back on this. Super useful sometimes to assemble things. You want to be able to remove the parts. So there are ways to laser cut specific shapes in which you can fit a nut and screw it with a screw on the other side of the panel. Now, super simple to do. You can design this as a block and copy it wherever you want it. It really takes seconds, but it allows you to make something that can be disassembled or just even opened, you know. Very often you don't want to glue everything together. That's actually a sign that something is going wrong. Same thing as we said, you glue things or you screw things, the concept is the same. You can be symmetrical or not. Here you see solutions for a pretty thick wood. When it becomes thinner, there's the risk that this hole gets too close to the line. So usually at that point, you design a sort of bump or extra material around the hole just to make it more robust, but it's a tiny detail. Now, this object is not laser cut, it's cut with a milling machine, but it gives you an idea of how to create connections that could make the object a bit more robust, having connections that are not at 90 degrees. Now, what happens when you have connections that are not at 90 degrees? It's pretty easy to see it if you think about a section of the object. So if I have my part that is at 90 degrees, this is the connection part, so this is the full part. The second object I want to assemble is going to be at 90 degrees. So this is the part that overlaps. This is the rest. So I'm just designing 2 pieces glued together basically and laser cut. Now it's not easy to design it on this, but just to give you an idea. Let's say something like this. Okay, so in this case you have 2 pieces at 90 degrees. The surfaces here, between here, this surface here, the surface on the back, this one here, and the one on the back here as well. So this entire area is perfectly overlapping. So it's very easy to glue these 2 pieces together. Now, when you change the angle, things change quite drastically. So if I have something that goes like this, for instance, and the second one is not at 90 degrees, but it's, let's say, a bit more. Now, the laser cut can only cut perpendicular cuts, at least the cheap one. So let's consider that a rule. That means that the cut in this case is going to be like this, and the cut in this case is going to be like this. Now, I know this is not super easy to visualize, but the only thing I want you to focus on is that when you're not in a 90-degree situation, you might have something poking out, and that's easy to solve because sandpaper is still a valid option with a lot of materials. But the main point is that now the only surface that actually overlap, that actually allows you to glue the two pieces together, is that one. So there's no contact anymore between these two surfaces or between these two surfaces. I know it's not super easy to visualize, but the point is very simple to remember. When you glue things together, okay, when you glue things together in this case here, what you get is tiny overlap in between here and here and here and here. Those overlaps will not be enough to give resistance to your mechanical part, to your object. So you need a third part perpendicular to both that could be properly glued along a pretty wide surface. So this is very important. In general, 90 degrees angle are the easier, but if you want or you need to do something different, it's not a big deal. Keep in mind you need to add a third piece that goes between the two and makes the connections resistant. Sometimes you have to assemble pieces not perpendicular to each other, but just flat. So this is common when you need to, glue together parts that are bigger than your laser cut area, but sometimes it's also a matter of optimizing the pieces. So, So we were saying this part here could be the connection between two elements to create something bigger than the laser cutter, or just a way to connect back pieces that were easier to cut if you divide them. Now, why do you have that weird shape? That weird shape, the finger connection, is actually very important when you work with wood. So wood has a pretty important characteristic that you should remember. So when you have a piece of natural materials like wood, it has veins and fibers all along the surface. Okay, and these veins and fibers are not behaving in the same way in every direction. So if I glue a piece next to it with the same or kind of the same direction of fibers, now this works very well because the fibers are aligned. So this connection here, if I glue the two surfaces along this line here, that should be working without any problems, without any particular treatments of the surface, because the fibers are parallel and the connection between parallel fibers is pretty resistant. That's not necessarily always the case. So it's actually not in the other direction. So when you have a piece of wood like this with the fibers in this direction, and the next one is glued here with the fibers, head to head against head here in this area here. So you have fibers head to head and not side by side. Now the connection in this case is not going to be resistant enough. The only way you have to make it more resistant is, instead of gluing this line here, you cut both borders with a zigzag line. Now what happened is that at this point the fibers get more parallel somehow. So you have fibers that gets up to this point, and in the other direction you have longer fibers here. So the connection here is going to be much more resistant. Beside that, you also make things, you also make the surface between the two parts much larger. So just to be clear, if we have two parts and we have a connection that goes like this, the finger connection as we said, what happens is that the fibers here touches the fibers in the other piece, mainly side by side and not head to head. And that's what's gonna make the piece more resistant. So in some parts, of course, there's gonna be head to heads, but it's a minimum part. And even more important, the gluing surface gets really big compared to what it would have been to a straight cut. So this is fundamental for wood, but it stays a good suggestion even for other materials. So think about plastic, or think about even MDF, that it's just fibers mixed in every direction. Increasing the surface, it's still a very good solution. And the second very good solution is to actually have pieces that slides inside the other piece and makes it more resistant to this kind of movement. So better gluing, but not just that. The second thing you see here that seems a bit weird is just a puzzle line. This helps because it's also more resistant than these solutions, of course. It gives you more surface to work with, and more mechanical interaction between the two parts. But it's harder to actually get, in particular because if you remember what we were saying before, when you have a line like this and you laser cut it, you get a gap. Okay, and in a geometry like this, when you get a gap that of course is not as big as the one I designed, the pieces can actually move a lot. They can move back before these two surfaces get in contact, and that means that you can use a puzzle. It's actually a nice solution to use, but keep in mind that you have to be very precise with this cut. It means that you had some test on your machine, you know the curve, the amount of material that the laser is cutting away, and you compensate in your design for that amount of material that you lose. As I said, there are fancy things you can do, fancy joints and fancy connections. I tried this out quite a bit, fascinating to use, but very weak. So I'm gonna skip this. If you need to have something that snaps together, we can talk about it. It's not gonna be the first choice for any of your projects. There are more resistant connections that you can create that works on friction in different ways. So my suggestion is to focus on those. On the other hand, this could be pretty nice. When you snap things together, when you connect parts together, very often you have to rely on glue or you have to rely on screws. But these snaps, these interlocked pieces can be very resistant. Some of the objects that you will design could have this as a technical solution. So the secret here is simple. the object will resist some stress because you pull it or you smash it or you do different things. Now, it doesn't matter the direction of the thing, the direction of the stress, but it should never be the one that opens the object. So you have two combined movements. You can see it here. This object slides in and then it rotates. After it rotates, it's not able of sliding back anymore. So this is really like a good way to assemble pieces and have them in the proper shape and in the proper position, and stays like this easily. Let's skip this. Let's skip this. So it's just that there are very nice and fun connections that you can make that comes from the traditional woodworking. You can do them with a milling machine. These designs come from that. You can do it with laser cutters as well. You just have to work with different layers. I don't think at the moment this is something that could be useful for you. Steel cutting, we are still on the basics of laser cutter. You can design simple mechanical solutions. For instance, you can design parts that can spin one compared to the other. Now, the most obvious spin, the most basic thing, is to have one piece with a hole and another one on the back, for instance, with the same hole. So if we put a screw in here and we screw the two parts together, of course, this element can rotate compared to the previous one. Very simple, nothing particularly interesting to say here. Things becomes a bit more fascinating when you work with parts that moves perpendicular to each other. So we are not talking about parallel parts anymore, but perpendicular parts. In this case, you have a box with a lid, and the lid rotates along this hinge here. Now, if you think about it, the lid of the box is probably cut this way. Okay, let's simplify it a bit. Okay, what you get here? Well, you get a part, this to be precise, that is basically a pin, a square part, and then it goes on. A square part that could rotate inside something. So that object, if we sketch it quickly 3D, will be something like this. Okay, so this part here can of course rotate into a hole, but what's gonna happen is that you have the side of the box and you have a hole on the side of the box, and inside this hole you have something that is not actually round, something that is square. So the part we've seen before, when you laser cut a straight profile, when you laser cut a profile and the cut is straight because that's how the laser cut works, what you get is a squared, different proportion maybe, but this is the concept, section. Now this section can't be considered good for moving inside the object, okay? Because it's definitely not gonna be the best way, and as soon as these corners wears off a bit, you get a lot of unwanted movements in there. So what could be the alternative? Well, the alternative is pretty simple actually. When we design the side of the box, we cut a circular hole. I made it a bit too big. Let's make it a bit smaller. Okay. You cut a circular hole, and inside a circular hole, a square hole. Now this part here, I will make it blue, works like a hinge. So because there's a gap between these two cuts, we know why, laser cut burns away stuff, there is already a bit of gap that goes all around this circle and the hole where I created the circle from. If I glue in the center of this, here, the piece that actually goes on as the lid of my box, then when I rotate this, when I open it, this part is the one that rotates, okay? And it's glued together, so at a certain point I will have the square pointing this way and my lid opening here. This is the easier way to make robust hinges of two pieces perpendicular one to each other. You can see it here actually. You can see the borders. This disc here is just that thing. It's just a way to create an intermediate part, something that can rotate, something that is glued to the lid. So it's perpendicular to the lid because it's the second part that we glue together, but that can easily rotate inside this side of the object. Next chapter will be, let's do like this. Let's finish with the mechanisms as well, and we'll keep the engraving for a second video. So focusing on mechanisms. Mechanisms can be easily done cutting parts and joining them together, but it's not easy to design mechanisms. So things that are animated could be tricky to do. Gears can be tricky to do. Understanding how to match things together could be complex. So a very nice website that I suggest you to play around with is this, 507movements.com. We can have a quick look at it. So it's basically a collection of movements from very simple one. The one that you see drawn in vectors is because they are animated, so very easy to understand. But you also have one that are not actually done with modern technologies, just old sketches from books. It's still fascinating to see how things works. And when you have to animate things, this could be really, really useful. Move things could be very, very useful. And you really have 507 different solutions. So you can really go around and have a look and see different things and, get inspired by different solutions and see the movement of the things. There's also a bit of history here or explanation of how it works. This could be useful to find the keywords to actually Google for extra informations in this thing. When you go on a bit, let's see. we are still on the gears. Pretty interesting, but not what I was looking for. Okay, at a certain point you get to articulated parts. Now you can easily understand how this could be laser cut. So you have the holes, you have rigid parts, you assemble them with screws and you get this mechanism. So even simple solutions can be done with lasers, or more complex one with gears, without gears. But first of all, you have, of course, to understand how things works. In my personal experience, that's the harder part in the design, not to make it with the laser. So, as I said, huge set of things. Play around, have a look. If you find something useful when you have a project that actually requires it. So this is it. I would say that's enough for today, or for this part about laser cut. The second part will be about other things that you can do cutting and what you can do engraving. So see you in the next video.